So now we want to take a look at the column to find out really how wide that should be, or excuse me, what its diameter should be. And if I was to click in here, just to give you an idea about how things are affected here, if I was to edit the type of the diameter of the column, and in this case, I realized I'd made an error when I first maybe set this up, is I labeled the column rate as a diameter and not a radius. So I would double check to make sure if you go into your actual element whether you're saying that this is a radius. I set it up to be a radial dimension, and then I called it a column diameter. So I've changed this, and right now I have this set for 10 inches, which gives us a 20-inch in diameter. And so if I went to something like a 20-inch in diameter column and applied it, you can quickly see if we needed to make a column that large, how kind of ungainly it would look, especially in steel. It almost looks like a tree trunk. So I think it's really critical that we determine that diameter to carry our load. And I'm going to just take a minute to set this back. So the way we're going to do that is to do calculations, and that's relatively complicated. If I was to go to kind of maybe the way you've learned it in structures to kind of review Euler's formula, the idea that a column has a buckling to it, which is basically the critical load that it can carry before it buckles. And if it's pinned on each end, it'll buckle its weakest form. If it's fixed on both ends, it gets a little bit stiffer. And these conditions are all generated or all inputted into a calculation where the critical allowable load on a column is related to a bunch of factors. Obviously, the material that we're using, in this case steel, the moment of inertia, which is the cross-sectional property of that tube that we're going to use, and then the length of the column, obviously, and the longer it gets, the weaker it gets, and that's a squared function. So it's very sensitive to the length of the column, and we're using really long columns, so it's really a critical kind of a determination. So this is a complicated formula many times because of really not just because of the basic math, but just the largeness of the numbers and the fact that they're just getting them all into the same units. So a professor at Cornell, I think he's now retired, John Ashorn, really created some wonderful calculators, automatic calculators. And if we go to structural calculators, if you go to his site and then go to the structural calculators, you'll find that he has columns and all kinds of columns here, but this idea of a steel column calculator. And if we click into that, this is a really very useful site or very useful calculator. It can take any kind of section type that you want. In this case, we'll take hollow structural steel sections, and we're going to use a pipe form, round, and I'll just pick one arbitrarily, a 10-inch one, and we want to set our length to 85 feet. And now I just changed this number, but I'm not going to hit return yet, because if you notice down here at the bottom, it says the capacity of this section is 144 kips. And now that was at 10 feet. So now if I hit return on this, it says that it's no good. It fails. It can't carry that load at 85 feet. So what I need to do then is to try and pick something that's a little bit larger. And this can carry, if I go to something now that is 18 inches in diameter, I can carry 142 kips. And if I max out, go all the way to the very large amount of capacity, we'll come up with a total allowable load of 196.6 kips. And I think it's really up to you to determine whether that is actually sufficient to carry your tributary load. So once you've done this calculation, I want you to use the snipping tool, and just as we did before, bring that into the Revit document. And I'll just jump out to the Revit document now, and I'll zoom out because I've already added these components. Let me deactivate this view. So here's the screenshot of that column calculation. And then I want you to write and it looks like determinations. isn't spelled right. Something looks wrong about it. I want you to write a little bit of a review about your project, kind of things that you want to tell your structural engineer if you met with them, things that were on your mind, the way you made some determinations. So here's some starting kind of statements. My beam is currently X deep and does or does not carry the load. What size is your column? State your column size. And then, is it slender as you want it? Will it carry the load? Won't it carry the load? In your analysis, these are the things that you want to discuss with your structural engineer. I want you to answer a question yourself. Has the analysis changed your thinking? That should be your thinking about the design. And what would you ask your structural engineer on the project? What are the questions that have come up in your mind as you've gone through the analysis? And then an overall view, has this been worthwhile? Is this a worthwhile methodology in order to prepare for the idea of having discussions with your structural engineer? How do you feel about the project? You have suggestions for ways to improve the project. I would love to hear any kind of dialogue that we can create. I consider this a really important part of the project deliverables. So we'll just finish up now with maybe adding some building underneath our column system in order to make it look somewhat similar to the original project and prepare it for submittal.